All right, very good. Yeah, so good afternoon, everybody. My name is Jari Pallari, and I'm here to talk about design automation. And before diving into this fascinating subject, I'm just going to give you a couple of points about Taika 3D. So we are a small software company in Finland, and we have been delivering various automation projects in the O&P sector for about 3 years now, and we've got customers all over Europe and North America. And so startup presentation. So I want to first talk about kind of why this design automation idea is necessary and why people are interested. Then I'm going to touch on how it's actually done. What do we mean by what is it in practice, and then a few thoughts on integrated design and kind of more complex design ideas and why those are relevant. So okay, yeah. So what do we mean by design automation? And if you've ever worked on O&P designs or any kind of scanned bespoke product designs, you know that there's a lot of if you need to make several bespoke products, there's a lot of repetition in how you make those. Like your product is exactly the same every time, but the geometry is different. So you have to kind of do it by hand, and basically design automation is just automating those manual steps that you repeat again and again. And usually you manipulate the input data, you clean it up, you fix holes, whatever. You then move on to manipulating that surface, for example, positive corrections and such like. And once you have your anatomy kind of, or your positive corrected the way you like it, then you can start to create the solid, the actual product around that. So that's what we want to automate, and that's kind of the field that I'm talking about. And why do we want to kind of do that? The key really is scalability. That if you do everything manually, it will take potentially a very long time, and you will be really bored. But you can't really turn that into an industrial product, industrial process that you can sell and put into the NHS or anywhere else by any stretch of imagination, because you need to be able to do things quickly. You need to be consistent and repeatable in your process. And also, if you can automate all of this kind of more basic stuff, then getting to the more complex stuff is going to be much more, well, you need to be able to do that as a prerequisite before you get into any of this more complicated things that I'm going to touch on a little bit later. So also, if you automate these things, you lose the chance of kind of making simple human errors. Also, if a system is designed from the ground up to design a particular product rather than being a general purpose design system, then you have it is much easier to use because you have 5 functions rather than 52. And also the possibilities present themselves to kind of change the way who designs the product, actually, because the orthotist or the prosthetist has the actual best information what the patient needs. So if you can have that person make the design decisions, the positive corrections, and like feature placements, if you can push that onto the, let's say, the tablet that they already have a mock-up, or they can see some kind of preview of the device, then you've already kind of moved all the important decisions to the person who should have the most control over them, rather than being some designer in the back office. So this becomes possible. And then obviously everything is measurable, trackable, and all that. And you can then integrate these kind of systems in as a part of your ERP system or product management system or invoicing or whatever. And again, if you want to scale this from like a one person, one computer process into an industrial process, this is what you need to be kind of thinking about. And then how do we do this? So we start with some kind of input data, and we then want to do something with this data, and export and manufacture, and then post-process. These last two steps are pretty much more straightforward than the first two, because you have service providers making components for thousands of customers every day using 3D printing. So this is kind of already in the industrial scale, whereas these two are not. So in terms of the input data, in the world of ONP, we're basically talking about 3D scans, surface scans. Very rare cases you have any kind of imaging data. And this is usually handheld scanners or plate scanners. And more recently, you have the Face ID scanner from Apple, which is certainly accurate enough for most applications. And once you have the input data in your system, then kind of what I previously mentioned, the positive correction. So here's an example of rear foot varus and valgus correction. So obviously you want to kind of grab that heel and turn that into the right position so that you have your corrected kind of corrected shape, and then you can move on to the the product generation itself, which is kind of the solid design. And you have two main kind of options or paths how you can go about it. And one is to kind of create your kind of perfect design. And then you basically scale that, you morph that onto your scan. And this has kind of certain limitations, because there are limits to these kind of morphing algorithms and how they can be implemented. And also you might need a whole range of templates depending on what kind of features and combinations of features you have in your products. So that might be a great solution for certain things. It certainly can speed things up, but it's not going to be a kind of a panacea. The other solution is much more I would say kind of versatile, but it is a bit more time consuming in terms of implementation and kind of processing. So you then create a trim line first, using usually anatomical landmarks around your input data, and then you kind of, once you're happy with that, you extrude that and you create a solid from that surface. And then you start adding different features or manipulations or what have you onto that. And here's just kind of a little example of how you would kind of define these kind of features. So this is kind of an a foot orthotic shell with a heel structure, and here we have a center of heel marker, and we also have kind of the X and Y axis. So here I could define my heel like okay, I'm going to take the distance between the back of the heel and the central heel marker, and I'm going to then take a certain percentage of that, and I'm going to go towards the distal edge, and that's where I'm going to draw my front of that heel post line. Then I'm going to define a certain distance from the edge, and then the outline of my my heel post is going to be X% scaled down in X and Y. So I create that line, and then I define the corners that connect these two kind of previously defined kind of geometries together. And then it could be that I take another view and start defining other roundings and things like this. So this is just kind of what goes on behind this is what the code does. And again, this is pretty straightforward. And once it's defined, it's in there. You only have to do it once. And then if you want to tweak it in the future, then everything is possible. It's just software engineering. just software engineering. That's like that's easy. Okay, then last point is the integrated design possibilities, and this is where all the cool looking stuff comes in. And I'd just like to kind of split that onto engineering and design. So engineering in terms of there's two things here. Finite element analysis is the first one, so you can quantify through these analyses. You can quantify actually what's happening in your devices. And where it's happening. So, for example, you could avoid kind of high stresses like this by adding material, and just knowing about these things and knowing what to fix is important. Then topology optimization can then help us further design more bespoke devices fit for a very specific purpose. The other system that I just want to refer to is dynamic musculoskeletal analysis, which can then bring in the human body onto the modeling system, not just the product. And we can then look at the interactions between the human system and the product, and how they interact together. But the question is kind of why? What benefit do I get from this engineering? And basically, I get a better functioning device. It's not just bespoke in terms of fit, but also in terms of function. We can be much more specific about that function and how it works with that specific patient. And that should impact the treatments, how effective they are. And also, through those analyses, I will have evidence that this has been engineered for this person, for this shape, according to these loads and these specifications, and here is what was manufactured. So this is a big change, again, from the craft approach. So we are now engineering these products. But there's always a but, and there's two things that need to change. One is that the engineers need to figure out how these tools are basically integrated into the workflow. So you don't need to take a separate piece of software and start learning FE analysis on a generic purpose FE analysis tool. That basically the solver is in your in your automation system, and you can do those analyses as you go along. And also the clinical side, people need to be willing to change and to improve how they work, and that's not as easy as it sounds. In terms of design, obviously we've kind of seen a lot of different complex designs. Some of these are more functional than other designs, so I'm not going to spend much time on these. But if you want to make these kind of things in scale, consistently, repeatedly, you get 100 orders every day. You can't do these by hand. You have to automate all of this design, and it can be quite complicated, as we can see from how elaborate these designs can be. And kind of maybe a final point here is that kind of that all of this complexity that we get, it should be used to add value and differentiate. So that if you have kind of a cool squid kind of design, then kind of why make just like a fairing that's like every other fairing out there, that you have the prosthetic still kind of inside? Why not differentiate? Why not really kind of just do more than just ape somebody else? And just so in summary, I think we all hopefully agree that there's lots of possibilities that we can, lots of opportunities to use 3D printed, and the freedoms provided, design freedoms provided, and more in engineering tools to create added value, new products, different products, better products. But on the other side, you need to be able to, for it to make any sense, you need to be able to scale these things up to industrial levels, and only then you will start to see these things in hospitals or all around the UK and all around the world, really. So that's my that's my 15 minutes of fame. Thank you very much for inviting me and for the opportunity to speak with everybody. Thank you.
No problems. Thanks, Jari. Just as a quick one, could you say how many personalized designs have been generated through the Taika software?
I don't have the numbers, but it's going to be tens of thousands at least.
Yep. So that's just a useful bit of scaling for people. That it's tens of thousands of people have received custom medical devices because you can automate the design. That's cool. That's excellent.